Oh. The cell file's gone. Hello and welcome to episode number 19 of CS350 Online. I'm your host as always, Leslie Eisted. In today's episode, we are going to do a little bit of review of our devices in I/O, and then we are going to dive into file systems, which is a pretty exciting topic as well. Just a few things just to remind you, and I know these are the same announcements as from Tuesday, but don't forget that you should get started on assignment 3 and the quizzes on Learn. Make sure that you don't leave those to the last minute. It's best that you do them as you go along. First, of course, let's talk about the OS of the day. So today's OS is one that you might have heard of. It's called Minix, and it was released in 1987, and it was developed by a gentleman by the name of Andrew Tannenbaum, who is also the author of one of the operating systems textbooks. It's about this thick. It's a giant one. I was actually using it as a stand for my camera before I got a little portable camera stand. So what is Minix? So Minix kind of stands for mini Unix because it is a Unix-like operating system, but it's mini in the sense that Unix is a monolithic operating system. That means everything in the kitchen sink that could be in the kernel is in the kernel, but Minix is a microkernel operating system, and originally it was written in a C, and there was only 12,000 lines for the kernel, file system, and memory manager. And that's really impressive. That's really, really small. I have certainly written software that is 2 and 3 and 4 times that size. So that is a really, really tiny kernel. So that's pretty cool, actually. Now, one of the kind of neat features of Minix is this concept of self-healing. Now, what does that mean? So many of you are probably running Windows. I don't know how many, but I'm going to assume that at least 25% of you are running a Windows operating system. And I'm going to assume that a lot of you have played games in Windows. And many of you have probably then encountered the NVIDIA driver crashing. And of course, it usually brings either a blue screen of death or it kills all the programs. It's not nice. Now, admittedly, I don't really run a Windows system anymore, so this is not something I have encountered in quite a many years. But I do remember this happening when I would play games like Warcraft 3, and the NVIDIA driver would just crash, and you'd either get a blue screen of death or whatever. But the idea behind self-healing is, wait a minute. The process probably didn't do anything wrong to cause the device to crash. Devices crash due to hardware faults. There's all kinds of different things that can actually happen to cause device drivers to crash. But what if instead of causing a blue screen of death, instead of killing the process, why don't we pause it, restart the device driver, and then let the process continue on? So that's actually a pretty good idea, and that's this concept of self-healing. It's the idea that we're not going to affect the running processes and have them crash when a device driver crashes. Now, I'm sure this isn't 100%, because certainly there are devices that if they crash, I'm sorry, it's going to have to blue screen of death. But this is still a pretty neat concept, and I don't think it's well done in many operating systems. I think it's been tried, but I don't know how successful this has actually been in other OS. So that's kind of a really neat feature of Minix. Now, what's really interesting is Minix is actually the inspiration for Linux. So Linus Torvalds was actually using the Minix operating system when he decided to create Linux. And there was apparently a lawsuit or something quite many years ago where they were saying, that Torvalds had actually copied a lot of the code from Minix and put it into the Linux kernel. But my understanding is that that is an unsubstantiated suit because the architecture in the code is supposedly vastly different. Now, I've never seen the code to Minix. I've seen the code to the Linux kernel. So I can't really comment on their similarity. But the one thing I can say is that one of them is a microkernel and one of them is a monolithic kernel. So that's a pretty big difference architecturally. Anyways. All right. So what I would like to do then is there was one last slide that we did not talk about last day, and I just want to do that last slide. It looks like I closed it because that's what I do. Okay. Just give me one moment and I will open that back up. Let's get that. We forgot to talk about, it's not that we forgot, I said I wanted to leave the last topic until today because it's kind of connected to today's topic, which is file systems. And that is this idea of persistent RAM. So we talked about disk drives, we talked about SSDs as being an improvement upon disk drives, but not like 100% better than a disk drive. In the sense that each cell can only be written to a fixed number of times, and that number is surprisingly small. It's only like 100,000 or so. And also, even though SSDs can technically keep their data without being plugged into a power supply, the mechanism by which they are able to do that will eventually lose power. Now, originally I had heard that was 10 years, but apparently in some more recent studies, some of the data can start to be lost in as little as a year when it's unpowered and kept in certain temperatures. So that's a really interesting thing. But I mean, if you haven't used an SSD in a year, you probably don't need the data on it anyways. SSDs are not good for archival storage. That's what I'm trying to say. There's one more kind of storage to talk about, and that is this idea of persistent RAM. So we talked about RAM under the context of it only manages to keep the values in it while you actually have power traveling to it. But there's a fairly new idea of persistent RAM, which is RAM that actually is able to keep its data in the absence of power. And there are various implementations of this. ReRAM or resistive RAM is one of the names. And 3D XPoint, also known as Intel Optane, is another one of the names. And what's interesting about this format of storage is that you can actually purchase this, by the way, now. But for consumers, this is not really useful because in terms of performance, the last time I looked at the numbers, it wasn't that much different than if you had a PCIe attached SSD, which is instead of like being attached over eSATA, it's actually like plugged into the motherboard directly and is a part of the PCIe bus. So my understanding is the last time I looked, the performance of this wasn't actually really any better than that kind of memory. So for a consumer, it doesn't really make sense. Where this kind of storage actually does make sense is in industry. So this is more of a commercial use. And the idea is that if you're going to traditional storage, i.e. secondary storage that is a mechanical hard drive, which is going to be larger and they're cheaper. Cost per byte is much, much cheaper for a mechanical drive than an SSD. That's really expensive. Like it's orders of magnitude more expensive, and now you should know how to calculate the cost of that, than going to an SSD or going to RAM. And so what they want to do is they use this resistive RAM, this ReRAM or Optane, as a cache. So you can't expand the size of the cache on the CPU because that's like actually it's hardwired. It's actually like physically a cache on the CPU. You can't change that. And you don't want to set aside too much of your RAM to use as a cache. I mean, some of it is set aside for caching certain things, but you don't want to take too much because then that's going to restrict how much multiprocessing you can actually do or how much RAM is generally available. So the idea behind persistent RAM is that we can use this as a cache for secondary storage. And what we're going to start talking about today is actually how we store files on disk. But the idea is, and I've briefly mentioned this in the last episode, is that we don't actually store files as one contiguous allocation, like solid piece of data onto the disk, because then we end up with fragmented disk where we need to save a new file and there's no contiguous space to put it. So we actually do something kind of like paging where we divide the file into a bunch of little blocks. and then the blocks kind of get scattered across the disk. Now, of course, that has the downside of being non-sequential I/O, which is why you have the defrag program to periodically run to kind of try to make the file sequential if you can. Not that we care so much about defrag these days, but so the idea is that this persistent RAM can be used to cache blocks of the file. So if you notice that your users on the network are accessing certain files frequently, that's going to be really expensive for you to keep going out to secondary storage to a mechanical drive to retrieve that. So the idea is that you can cache parts of the file in this persistent RAM, and then it will be faster. So it's not as fast as getting something from the CPU cache, and it's not as fast as getting something from RAM, but it's still pretty darn fast compared to mechanical storage. And the other advantage is that, and this is a big advantage that persistent RAM has over storing your file blocks in a cache in regular RAM, is that if the computer restarts, like let's say you lose power and you fire the machine back up again, that block cache still exists. So the next time you boot the computer up, presumably the user behavior will be the same and they'll want the same blocks of the file. Well, good luck, because you stored it in the persistent RAM, which means that all of that cache data is still there the next time you reboot the computer. So you're not starting from an empty cache, which is kind of useful. So this is kind of a really neat thing. It's not, like I said, I don't really see this right now as being really useful for home users of computing hardware, because most of us are happy with like the SSDs that we have in the disk in the computer that we have. And I mean, for me, so I have two big NASs. One's a backup of the other one, obviously, but like I'm attached to that over a 10 gig Ethernet connection. And it's not like I use it for media access, but it's not something that's, because there's so few users on it, it's not a big deal. There's not really lag. But if you've got a whole bunch of people using it, then something like this would actually be useful. All right. So what I want to do now is actually do a sample problem. And this is, again, in the batch of sample problems that we've posted on Piazza. And so this is called Disk I/O. And what we've got is a server with a single disk drive and a single core processor, just one of them. And what I want to know is, given some number of processes are running, I want to compute the CPU utilization if every process is running the same piece of code. And the process is running this piece of code that does 5 milliseconds of compute followed by an I/O operation. And it does this repeatedly over and over and over again. So what is the CPU utilization? Remember that the CPU is going to be idle while the disk is doing the I/O service request, because the user process is going to have to wait for the I/O operation to complete before it can continue its computation. So we need to be able to compute the length of the I/O service request. So we have the information about the disk. So we have a block size. You'll notice we're using blocks instead of segments. That's totally fine. What we actually do with the disks is we actually take a number of segments and we group them together into a block. And what's interesting is our block size is usually equal to our page size, so that when we're doing on-demand paging, it's a single I/O request to grab one of the pages of the address space from the disk instead of like 8 I/O requests. So that's going to speed things up a fair bit. All right, so we've got the block size, we've got the total capacity of the disk, the number of tracks, we have the average seek time, and the number of rotations per second. So now we need to figure out the CPU utilization when there's only one process. So the first thing I want to say is, in order to do this problem, we actually need to, before we can compute the CPU utilization, we need to actually figure out how fast an I/O service request takes on this disk. So let's start this by saying, actually turning my tablet on. It's always a good place to start, right? It's connected and it's powered up. So the first thing I want to know is the rotational latency. So we are given that it does 100 rotations per second. Okay. So how long does it take to do one rotation? So one full rotation is 10 milliseconds. Okay? Which I'll let you figure out how to do that calculation. You're just going to, if you do 100 rotations per second, then you're going to figure out, then you can do one rotation in X seconds, which ends up being 10 milliseconds. Okay. Now, this is only useful if we know, so if we're trying to figure out the rotational latency and we want to know the exact rotational latency, then we would need to know the sector we are starting on and the sector we are ending on. And we don't know any of that information. We also know that the platter is constantly spinning. So really what we want is the average rotational latency to use in our formula. So average, I'm going to start short forming here. The average rotational latency is the max divided by 2. So that's going to give us 10 over 2, which gives us 5 milliseconds. And then we need to know, since it doesn't tell us what track we are on and what track we need to go to for these I/O operations, we're going to use the average seek time. And that is actually given in the questions. So the average seek. And again, if you're looking for these formulas, these are all in one of the little extra notes that's posted on Piazza. So we are given the average seek time as 5 milliseconds. And actually a lot of drive manufacturers, they will either give you the max seek time or the average seek time. This is a pretty good seek time. If you're looking at a consumer disk, the maximum seek time is usually between 9 and 12, sometimes higher milliseconds. And on a commercial or a higher end drive, it can actually be as low as about 4 or so milliseconds. But that's another story for another day. Okay, now we need to know how much of the track we are transferring. So it says the I/O request is going to be 1 block of data. But what fraction of the track does that correspond to? Because I need to know that in order to figure out what is the transfer time. So I need to figure out how many bytes of data exist per track so that I can figure out how many blocks are on each track. So let's figure out the capacity of a track. So the capacity of a track is going to be the disk size, which here we have as 2 to the power of 27 bytes. So that's 128 megs. And we're going to divide that by the number of tracks, which is 2 to the 10. So that gives me 2 to the 17 bytes per track. And now that I know that, I can figure out how many blocks are on each track. So blocks per track. I know that my block size is 2 to the power of 12 bytes. So I'm going to take the capacity of the track, which is 2 to the 17, and divide it by the capacity of a block, which is 2 to the 12. And I know that there are 2 to the power 5, or 32 blocks per track. That's not so bad, right? I think we're all okay there now. So in order to transfer one of those, so our transfer time is equal to 1 over 32 times the maximum rotational latency, which was 10 milliseconds. So we get 10 over 32. So just for the sake of discussion, we're going to say this is about 0.3 milliseconds. So now let's compute the cost of an I/O operation, or the I/O service request time. So our I/O service request is equal to the sum of these things. So we've got 5 milliseconds. This is our average rotational latency, plus 5 milliseconds for our average seek time, plus 0.3 milliseconds for our approximate transfer time. And you don't have to be precise here. This is approximate. So you're getting about 10.3 milliseconds for an IO service request time. So what happens? Oh, I just love it when this program breaks. Oh, that's so hilarious, except it's not. All right, so now based on this, we want to compute the CPU utilization. So I'm actually going to close OneNote and then reopen it so it'll stop acting stupid. Yes, I know. So our IO service request was 10.3. Okay, now what we're going to do is compute the CPU utilization for a single process. So the program does 5 milliseconds of compute followed by an IO request, and it repeats that. So let's say P0, because we only have one process, it does 5 milliseconds, and this is our compute time. And then 10.3 milliseconds, this is our IO. And then this is going to repeat. So 5 milliseconds compute, 10.3 milliseconds IO. Now, why doesn't the process do its next compute cycle during the IO operation? Because probably the next IO operation depends on whatever you did, or the next compute cycle depends on something you did in the IO operation. So to look at the utilization, I'm going to take this repeating block, which has a total of 15.3 milliseconds. And the CPU utilization is going to be what percentage of that time is the CPU actually doing something. So that's our compute time, which is 5 milliseconds. So we end up with a compute time, or a utilization of roughly 1/3. Now, in the next part of the problem, which of course OneNote's crashed again. It's such a lovely program. In the next part of the question, we actually have two processes, P0 and P1. So we're going to do, P0 always starts first, and it does its 5 milliseconds compute. And then it does its 10.3 milliseconds I/O. Now, while it's doing its I/O, process 1 can do its compute. Now, you might be saying, and then it can start its I/O operation, except it can't, because you can only do one I/O operation at a time. So this actually has to wait. And it does its I/O operation down here. And while process 1 is doing its I/O, process 0 can do its 5 millisecond compute. And then it has to wait. And then it does its I/O here. Okay. So the repeating block here is a little bit different. The repeating block, and we can ignore the head and the tail. We're looking for the average utilization. So our repeating block is actually this here. And I've just circled in red. And if you look at this, for every 10.3 milliseconds, we do 5 milliseconds of compute. So the utilization here is about half. Now, if you want to take this even further, try this with 3 processes and 4 processes. And if you want to take it even further, figure out if it's possible to get 100% utilization. And if it's not possible to get 100% utilization, what is the maximum utilization that you can get? So if you want a challenging problem, there's one for you. All right. So with that, what I would like to do now is actually move on to our new topic. So for those of you following along with the course notes, we are now moving on to the file systems slides. And again, these are posted on the course website, so don't worry about that. So we've talked about how the disk works. We've talked about how we interact with the disk. We've talked about the costs associated with interacting with the disk. But the thing that we haven't actually talked about is how is the data actually stored on the disk? How do we actually store files? Because it's actually quite interesting. So files are the persistent data that we want kept. It has a name, and what's interesting is a file, in addition to having just the actual data of the file, has a bunch of metadata associated with it. And the metadata is actually quite important. The metadata is stuff like a timestamp as to when the file was created, and a timestamp as to when the file was last accessed. And things like who is permitted to read it, who is permitted to write it, who is permitted to execute it, and so on and so forth. So files are the persistent data that we're actually storing. But it's not that simple, because if we just store our files on our disk, how do we find them again? So there has to be more to it than just, I've gone on BitTorrent, I found my favorite movie, and I downloaded it, and I put the file on my disk. I actually need to be able to retrieve that file at a future date, because presumably if it's my favorite movie, I'm going to want to watch it more than once. And this is kind of where file systems come in. So the file system is all of the data structures and algorithms that are used to store the files, retrieve the files, and control access to the files. And if you look at file systems, they can be divided into 3 different layers. There's the logical file system, which is a really high-level API, and that's what you've interacted with. So if you've ever opened a file, written to a file, read data to a file, copy and pasted things in between, your C drive and your D drive, that's the high-level logical file system that you were using. And it's very rare that you would use directly anything that sits underneath. Now, underneath the logical file system is an optional layer called the virtual file system. Now, when I was a kid, this wasn't something like this was not a common thing. But what the virtual file system lets you do is it's going to take a whole bunch of different disks or storage mechanisms, and it presents them to the logical file system as one unified thing. Because when the logical file system, when you're interacting with the files on your computer and your attached storage, you shouldn't have to use different tools to interact with, your NAS. By the way, if you're not familiar with the term NAS, it's network attached storage. So I've got a great big NAS, and I don't know, it's something like 60 terabytes or something like that. And I shouldn't have to open a specific web app or something in order to interact with my NAS. I shouldn't have to open a specific software for that. All I want to do is I want to open up, my file thing, and I want to say, oh, here's my NAS, and I'm just going to use whatever this tool in Apple is called, File Explorer, I don't even know. I don't want to have to use a special tool. I just want to use the same tool that I use to interact with the local files as with the remote files. And that's what I can do. So this is the virtual file system presenting all of the other underlying file systems as one thing to the logical file system. So me, the user, never has to know that I'm technically interacting with different devices or different file systems. And I am interacting with different devices and file systems because this NAS here does not run APFS. It's not running an Apple file system. It is not running NTFS. I'm pretty sure it's running exe4 actually. So, but I don't need to know that because it's been abstracted for me by the virtual file system. All right. Let's make sure I actually click on the right thing this time. So, and then underneath the virtual file system, you have the physical file system. And this is how the files are actually being stored on the physical media. And what's interesting is when we think about file systems, we don't think about the logical file system. We don't think about the virtual file system. We actually think of the physical file system, even though that's not something we actually directly interact with. So when we think about when we think about file systems, we think of words like APFS, which is the Apple file system for SSDs. We think of things like NTFS, which is the journaled file system that Windows used. We think of ext4, which is a journaled file system that Unix systems tend to use. Or if you have a really old computer, you're thinking of FAT32, which is an old file system that Windows used to use. So what's interesting is those are the names of the physical file systems, and that's how you're actually storing the data on the physical disk. But when you interact with those disks, you're interacting with them through the logical file system. So you don't actually need to know it's a FAT32 system. Okay. It is helpful to know that because there are restrictions, but it's kind of an interesting thing. Now, there are all different kinds of physical file systems out there. So I've mentioned a few of the common ones. So FAT32 is probably the most common file system on the planet. It's also the easiest to interact with. And what's interesting is it's very restricted. So FAT32 actually has a maximum file size of 4 gigabytes. And if you ever go to like Canada Computers and buy like a USB key or a little micro SD card, chances are the default file system that's been set on that is probably FAT32. And if you try to, say, copy a 40 gigabyte movie file over to it, it won't work. And it won't work because FAT32 does not support 40 gigabyte files. So what you have to do is, if you want to maintain the compatibility of FAT, there's another file system called exFAT, which lets you have bigger files. And of course, NTFS and ext4 and APFS let you have much, much, much bigger files than that. And there have been lots of files that we've used over time. So ext1, ext2, ext3. Back when I was in undergrad, my favorite file system was one called RiserFS, which I think was the first journal file system for new Linux systems. And if you could get it installed and running, it was actually really, really fast and really reliable, but it was a bit tricky to get it working at first. Nobody uses that file system anymore, and you may not have ever heard of it. And the reason for that is actually because the guy who made the RiserFS file system actually murdered his wife. So that kind of became taboo. But my understanding is a lot of the innovation that was in RiserFS actually made its way into the ext series. Anyways, who said computer science was boring, right? What other file systems might you have heard of? There's the log file system. There's Amazon's S3, which is a log central file system. There is FAT16 and FAT32. There's so many. And of course, before Apple used APFS, which came with, I think, Catalina or High Sierra, they used one called HFS and HFS Plus, which they still recommend for regular drives, i.e. not SSDs. So there's lots of different physical file systems out there. Some of them have restrictions, some of them don't. But there you go. All right. So what I want to do today is we're going to start by looking at the logical file system. And this is something you know pretty well already. You just maybe didn't know it was called the logical file system. So this is going to include things like open and close and read and write and seek, and also a bunch of metadata functions such as fstat, chmod, and things like that. So what actually happens in each of these different things? So open is actually a really interesting function. So what it does is it takes a path, which is a string, and it's going to find the file. Now, in your computer, your operating system does not want to refer to files by these long-ass path strings. Your operating system would prefer if files were all referred to by some unique integer so that search was a lot faster. And in fact, that is what happens, is we refer to files by their paths, but that's really just for the human, for finding the file. The file itself has a unique identifying number. And after you've done the initial search to find that unique identifying number, from that point forward, we will only ever refer to the file internally by that number. So when you open a file, you're going to translate the path into finding the file and its unique identifying number. And then what's further interesting with open is that open is going to update the kernel to tell the kernel, hey, another process has this file open. So the kernel will have an open file table. And in the open file table, we'll say, okay, foo.txt is now opened by one more process. And then in the process has what's known as a file descriptor table. And in the file descriptor table, we will add a descriptor or handle for the file we just opened, which will include things like the file's unique identifying number and at what position are we at currently in the file. And if you've just opened the file, that position is obviously going to be 0 because you haven't done any reading or writing yet. Some other things that happen in the open operation is open is also going to be verifying that you actually have the correct permissions to open the file. Now, when you close the file, you are going to invalidate the process's file descriptor for that entry. So the handle that the process had for that file will be invalidated. It will be removed from the table. And then the kernel, its open file table, it will remove 1 from the number of files it has that file open. And if it's 0, we can actually remove the whole entry from the open file table. Now, what's really, really interesting with this is many of you, I know you plug in external storage. So you have like a little device, you plug it into your computer, like a little USB device, and you copy some data to and back from it. And then instead of doing a safe eject or safe unmount, you just pull the plug. Don't do that. Sometimes things get cached. So if you're writing to that disk, and you're like, oh yeah, I think the write's done, I'll just pull it out. The write may not be done. So writes don't necessarily happen the second you ask them to happen. Sometimes the writes get cached. And what can happen is if you don't flush that cache out to disk by closing the file properly or unmounting the file system properly, the last write operation may never complete. And so your file might actually be corrupted or not there. And I've seen this happen 100 times, millions of times. You should really be unmounting. Now, I know in Windows, it's so tempting not to do it because you'll be like, okay, I've closed my program, I've closed the file, and you'll say, okay, safe unmount or whatever it's called in Windows. And then Windows will be like, no, you can't unmount this because somebody's using this. And you'll be like, but I'm not using it. Oops, that might be a little bit of a bug in Microsoft's kernel. Somebody still has that file marked as being open. It's a pain, I know. All right. It's important to use close in your files, in your programs is what I'm trying to say, because close is going to initiate that flush so that the file actually gets written out. And the same thing with the safe unmount and the safe eject. It's going to make sure that any writes that have been cached actually get flushed out to the disk before removing the file system. So make sure you do those things. Otherwise, you can actually cause problems. Now, read and write are really interesting. If you read or write to a file, have you ever noticed you never tell read or write where to start the read or write from? You never do. So how does it know where the read and write are happening from? Well, remember when we open the file, we create this file handle in the process's file descriptor table. And in that handle, in that descriptor entry, one of the things that we have is the current position in the file. When you do a read or write, they happen sequentially from your current position in the file. So if you open the file and then read 20 bytes, you would be reading the first 20 bytes of the file. If you then do another read of 20 bytes, you would be starting at the 20 byte mark and you would be doing 20 bytes from there. So as you read or write, you are moving your current position in the file, and each read or write happens from the current position in the file. Now, what happens if you wanted to read or write from a random place in the file? Well, that's where this lovely thing called seek comes in. What seek does is it doesn't touch the file itself, but it touches the file descriptor entry in the process's file descriptor table, and it changes the current position in the file. So if you want to start reading from byte 10,500, you would seek 10,500, and it would update the process's file descriptor table to have that file's current position be 10,500. Now, here's a really interesting thing about seek, and this is, by the way, true in even like Linux operating systems, is that seek doesn't check whether that's a valid byte of the file. So you can seek way beyond the end of the file, and nothing bad happens. There's no error. The error would happen when you do the subsequent read or write, when it realizes, oh crap, this doesn't even exist. So seek doesn't actually check to see if you sought to a correct place in the file. So that's an interesting thing. And then we've got all of these lovely functions to play with metadata. And these are functions that you haven't probably, used in your code, but you have used from a command line. So let's actually play with some of them. Okay. So I'm going to go over here to a terminal. I'm playing with some Python code right now. Not that I like Python, but all right. So we can use different commands to look at files. So let's look at the files in my disk. I can use ls, and ls gives me the list of all the files in this directory, but it doesn't tell me much about them. It just tells me their names. What if I want to know more information about them, like how big they are, who created them, and what their permissions are? Then I do ls-la, and that is actually going to read the metadata for each of those files and display it to me. So I can know that I created main.py on March 23rd. So I created this file 2 days ago. And it looks like I created it at 1 in the morning. That's pretty normal. And it is 1,388 bytes. And it looks like the permissions on this file are everybody can read, write, and execute it. It's on my own computer and I don't care. Then I have this file 091_L and 091_R. These files were created on October 25th, 2011. Wow, these files are 10 years old. And they're quite big, and everybody has permission to read them and execute them, but only I have permission to write to them. So I am reading and accessing the metadata. What if I wanted to change some of the metadata? So some of the metadata that you can change is the permissions. So let's say I wanted to give everybody read-write permission to these two image files, which, by the way, this is actually a stereo pair. So the L image is the left eye's image, and the R image is for the right eye. Do stereo 3D work. So of course I have these images. So I can change the permissions. There's a function called Chmod. Now there's two different ways you can use this. There are numerical codes, like 777, to give everybody permission. But I don't find those numerical codes very readable. So newer versions of Chmod, which is like everything for the last 15 years, 20 years, you can actually specify the permissions you want to change. So I want to change user, group, and others, and I want to add write permission. Now, technically, I already have write permission to the user, so I don't need to do that. I can just do GO plus W, and then let's do 091L.jpg. So there we go. Operation not permitted. I wonder why that is. When it doesn't want you to do it, there's always giving it sudo. I don't know why it's not letting me do that. All right, let's choose a different file then. Let's choose raw.png, which is an output file I just created. So let's change its permissions. I have a feeling it's because those files were created on a camera and there's a bit of an issue there. Anyways, UGO plus write, and let's add that to raw.png. There we go. Now I do ls-la, and you can see that raw.png now has everybody with write permissions. That's pretty cool, right? What other kinds, of metadata can you change? You can change the user, you can change the group. There's all different kinds of things that you can change. Let's change the timestamp. So you might notice if you accidentally submit things in the incorrect file, we want some pretty specific proof that you haven't edited your file since the deadline. And we don't accept timestamps. Allow me to show you why we do not accept timestamps, because there's a very, very good reason we do not accept timestamps. So let's say that you had a project, let's say it was your thesis that was due to your supervisor, and it was due, January 2nd. And you didn't finish it on time. And then a few months later, when your supervisor finally gets around to say, hey, I should read my student's thesis and, start grading it, or not grading it, start editing it to make sure it's going to pass the defense. So, it's March, and you're like, wait a minute, I can't find my student's thesis. Did they not send it to me? So your supervisor sends you an email. Hey, I can't find the thesis. You were supposed to have this to me by January, 2nd or maybe January 10th. And then you respond to them, oh, well, I finished that back in December. I wonder if the email got lost and you didn't get it. In reality, you didn't finish it. So that, and you tell the supervisor, I'll send you another copy. But you want to make them believe that you finished it on time, and it was something to do with the email system that caused the problem. So we create our thesis file. We rapidly do it. We were almost done anyways. So we would take it a few extra months. And then if you look at the timestamp on this file we just created, you'll see it was just created March 25th at 10:18 a.m. We need to fix this. We need to make it look like we actually did this on time. So what's a good day to have finished it? Well, let's suppose instead of it being due in January, let's suppose it was due March 1st. So you don't want to be the person who created the file on March 1st. You want to show it was created before March 1st because you don't want your supervisor to think you left it to the last minute. So let's suppose you finished the file, created it end of February, somewhere in the mid-February. So let's change that. So we're going to use this command called touch. And so your thesis was due, let's say, to make things easy, March 25th. So it was due today and you didn't submit it. And you want to make it look like you finished it back in February. So let's make it the month February. Let's suppose that you finished it. If we use 25, it's too suspicious. So let's say that you finished it on the 27th of February. And let's say that, you've got to choose a time. If it's a multiple of 5 or an even time, that looks too fishy. You don't want your supervisor knowing that you stay up all night and sleep all day. So let's make it look like you're a morning person and you created it maybe at, 10:53. That's a good time. And now when I look at the timestamp on thesis.txt is now February 27th at 10:53 a.m. And so you conveniently send that to your supervisor and they're none the wiser and they believe that you actually did it on time and something happened in the email. Okay. This is why we don't accept timestamps, because it's trivial to change them. There we go. I don't want that file hanging around in my directory, so I'm going to get rid of it. All right. RM, by the way, is another part of the logical file system to remove a file. Okay. So we've talked about how your file descriptor in the file descriptor table keeps track of the file position. And it starts at 0 when you open, and then reads and writes are sequential from the current position in the file. And each read or write is going to update the current position as it happens. And then if you want to do non-sequential I/O, you use the seek operation. But remember that it doesn't actually validate that the byte that you want to start from is valid or not. That will happen in the read or write when it throws a nasty exception and says this is an invalid position. So what does that mean? So if we were to actually do this following little snippet of code, and I'm actually going to try to show these at the same time. Yeah, I've been using these computers for quite a while, and I don't remember any of the shortcuts still. So here's our little snippet of code. And if we were to do what this code was doing in OneNote, let's just follow along. So we are reading the file 512 bytes at a time. So you'll notice that in read, we pass the file descriptor, the handle that we get from open, and then we pass the buffer where we want the data to go to and how much data we are reading. So if our file looked like this, A, B, C, D, E, F, and let's say instead of 512 bytes, we were reading 3 bytes at a time, then how we are reading these files is we read ABC first, then DEF, then GHI, and then JKL. So we are always moving in this direction. And then if we wanted to do things differently, we would use the seek operation. So what this one does is instead of reading them 3 bytes at a time starting at the front, we're going to do it 3 bytes at a time starting from the back of the file. So we seek to the last 3 bytes, read it, and then go to the second last 3 bytes and read it. So the second little snippet of code that's using lseek to seek to the position we want to read from actually reads the file, end of the file, this byte, block, and then this block. So it's kind of reading it in this direction. So that's kind of neat, right? So if you want to do any kind of like random I/O, you need to use the seek operation. All right. So now we need to talk about how to actually retrieve files and what are paths and what is a directory. So a directory is in itself a file, but it is a special kind of file. A directory is going to map the name of the file to the unique identification number for that file. So for example, if we have a directory foo and it contains a file blah.txt, that's for the human. And we need a way to translate blah.txt to the unique identifying number that blah.txt actually has in the file system in kernel. And that's what the directory does. The directory maps the human readable file name to the I number, the unique identifying number for that file. And what's interesting is you can actually open directories because they are a file. You can open them in VI. Now, if you do this in a Unix-based operating system, you will see the contents of the directory, but you will not see the I numbers. But we can do it here, so I don't actually have any directories in here. So let's go up one, and let's open the scripts directory. So the scripts directory, and what you can see here is that this contains that one little Perl file for the script for this that's contained in this directory. So it's containing, you don't see the I numbers, but you can still see what files exist in this directory. So each directory is going to contain what we call a hard link. The directories, this link is a mapping between the human readable name of the file and the I number. So we have a question on Twitch here. If we seek to the middle, do we continue reading forwards or backwards? So you always read forwards. So read and write always advance. They go forwards. They never actually go backwards. So if you wanted to read a file backwards, like truly backwards, you would have to seek to the end, read 1 byte, and then seek to the end -1 and read that byte, and so on and so forth. Now, some logical file systems may actually offer a high-level API function to read a file backwards, but not all of them do. Yeah. And some languages like, so Fortran, which I've done a fair bit of Fortran code, actually has a command called rewind, which actually lets you move the file pointer backwards. So if the file pointer is at like byte 512, you can rewind and it will move the pointer backwards. So that's an interesting thing. Now, why does it have a rewind command? Technically, because rewind traditionally actually meant rewind the tape drive. But now it just means move the pointer backwards. So there's a lot of different API functions depending on your language and your system. Okay. So directories are going to contain these things called links, which map the name of the file to its inumber. And that is what is actually contained in the directory. And then what's interesting is if you take all of the directories, they actually make this tree structure. So starting with the root, which is a directory, the root file system actually contains a bunch of things. And then each of those directories contain a bunch of things, and so on and so forth. So you get this hierarchical namespace tree. And that is the structure of how you find all the files on your disk. So the path from the root of the tree to a leaf or internal node, the path that you take is the human readable path. And so if we wanted to find, when we open, let's say we wanted to open foo misc temp, we would say foo misc temp, and so we start at root and we go down foo. We open directory foo to find the inumber for misc, which is 93. We open file misc now to find the inumber for temp, and then we get the inumber for temp, and then we can open file temp. So it's the directories that are doing the storing the information we need to actually find the data on our disk. Now, some interesting things. Remember, directories are technically files. They're just special files. And only directories can be internal nodes. Files themselves cannot be internal. Directories can be external nodes as well, because a directory doesn't technically have to contain anything. I mean, if you go on your computer, I'm sure you can find at least 20 directories that contain nothing. That's pretty normal. So directories can be leaves or internal nodes, but files can only be leaves. They can only be external nodes. So we can't have one of these square ones on the inside. And when you open a file, what you are literally doing is you are opening each directory in turn to find the inumber for the next path. So you're mapping from the component of the file name to get the inumber for the next part. So that's pretty neat, right? Now here's an interesting thing. You noted that I actually opened the directory in VI. I can't write to it. I can't modify it. So let's actually go over here. And let's open this scripts directory and let's actually try to write to it. So you notice it kind of opens funny. Wait a minute. It didn't let me edit it. So I was in VI and I tried to edit the file and it ended up navigating the file system. It didn't let me edit because you can't, as a user, directly edit a directory. I can't start writing. I can't even go sudo vim scripts. I can't start editing this. Like I can't, you see, it's not letting me. It actually just starts navigating. Why can't I do that? Why can't I write into the directory? Why can't I modify the directory directly as a user? Because this is a really bad idea. If I can do that, I can change the mappings between the file names and the inumbers, and that would be really bad. Because I would mess the file system up. So we don't let you do that. Users are not allowed to do that. The only way that they can change things that are in a directory is by using the logical file system's high-level API, like make mkdir and rm and open and touch and things like that. So you cannot otherwise directly edit. And all of those other commands, like touch, are going to correspond to system calls where the kernel does it on your behalf if you have the correct permissions to do so. So you can't mess your file system up by modifying directories directly. All right. And even if you're like, but don't I modify a directory directly when I change its name or when I move things into it? No, those are still corresponding to system calls that are going to check for permissions and do it properly. And that's a good thing. So we call those mappings, as I said before, a hard link. And here's something that is really, really interesting about it. You can have multiple hard links to the same file. A hard link is just mapping a name to a number. You can have multiple names mapped to the same number. So in this namespace tree, you can actually see the file number 147. There are not two files 147, but file number 147, of which there is only one of, there are two ways to get to it. You can get to file 147 from docs a.txt. That's a valid path to file 147. And foo my a is also a valid path to file 147. You can have multiple hard links, and you can create them using this link command. And that will create a new hard link to your file. And each file, as part of its metadata, actually keeps track of how many hard links there are to each file, because you only truly delete a file when there are no more hard links to that file, because then you can't find it. If there's no hard links to the file, then we can't map the name to the number, which means we can't find the file and it should be deleted. Now, here's some interesting things. We do not permit multiple hard links to directories. And the reason for that is we don't want there to be cycles. What can happen with the cycle? So let's get a new page here. Annoying OneNote. All right. So let's say we have directory foo. And foo is number 87. And inside directory foo, we have a mapping for directory bar, which is going to be 71. And then we have a file t.txt. And that's going to be file, 352. And then let's say in directory bar 71, I have a link to foo, which is 87. How many paths to t.txt exist? Well, there's foo t.txt. There's foo bar foo t.txt. Foo bar foo bar foo t.txt, and so on and so forth. There's an infinite number of paths to t.txt. That's not good, because if you automatic go to all my files, it's going to take forever, because it's going to travel every path in the tree and it's going to get caught in this loop and never finish. So we don't permit multiple hard links to directories. Now, it's not that every multiple hard link to a directory is going to cause this loop here, a cycle, but do you really want to have cycle finding, cycle checking stuff in your operating system, or you just want to ban it so you don't have to do any of that extra work? It's your choice. And that's the beautiful thing about operating systems is, yes, we're saying we don't permit this, but you could implement this any way you want. You could permit multiple hard links, and then you could just do cycle checking. You could implement it that way if you really wanted to. You are free to create an operating system however you choose. All right. Now, what is unlinking? So the process of unlinking would be opening up a directory file and removing the mapping from the name to the I number. Now, if there's multiple hard links to the file, then you don't delete the file. And that's why you need to keep the number of hard links to a file in the file's metadata. If, however, you are unlinking you're removing the last hard link to that file, then that unlink operation must delete the actual file. And what does it mean to delete a file? Doesn't mean what you think. So let's say you've downloaded something that's maybe you shouldn't have downloaded. Maybe it's a little bit secret. You don't want anybody to find out about it. And so you want to delete it. And you're thinking, I'll hit delete and it'll magically disappear. Does that actually mean the data to the file is gone? Probably not. What delete usually does is it's going to remove the hard link. It's going to mark whatever data blocks the file was using as now available, and mark the I number that the file was using as now available to reuse. But the actual file data that you didn't want anybody to see is probably still there. When you delete a file, it doesn't usually delete the data. And that data usually stays on your disk until that area of the disk gets overwritten by something else. So if you want to make sure that something you download and you don't want anybody else to know about can't be ever retrieved by like a forensic scientist, make sure you secure delete your files. Because if you don't secure delete your files, guess what? The data's still probably recoverable. It's kind of a weird thing. And that's why, let's suppose you're selling your computer or you're selling a hard drive. There's two ways you should format your disk before you do that. But don't do a quick format. I mean, yeah, a quick format takes like 30 seconds. It takes 30 seconds because it doesn't actually delete anything. You have to do the low-level format, and you should do it several times, especially if it's a mechanical drive, because if you don't, the data will still technically be there. Actually, there's this thing that they say that on a mechanical drive, it actually takes 7 overwrite cycles to truly remove the original data that was stored there. So it's, I mean, if you want to get rid of a hard disk and you don't want somebody to be able to retrieve the data off of, what most companies will do is they will shred the disk so that it's physically not recoverable, or drill holes in it and things like that. This is where you get to take your frustrations out, right? Fun stuff. All right. Now the last topic I want to very briefly cover today is the idea of multiple file systems. So what does that even mean, multiple file systems? This is the virtual file system, which is optional. And this is, how do you present multiple file systems to the logical file system as one unified thing? And different operating systems have handled this in different ways. Windows handles this by having file names have 2 parts. So in Windows, you may have noticed, I'm going to open a new page here, that a file on your hard drive is C:/ blah, 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 some path to blah.txt. This is actually a 2-part file system, or 2-part path name. This C:/ is identifying which file system the file is on. So that internally, if you've got some namespace tree, this is the C:/ path, this is the D:/ path, this is the E:/ path, and then there's the namespace tree for that, and the namespace tree for that, and the namespace tree for that. Now, how many of you have ever wondered, why is the hard drive in Windows C? Why is it C? What happened to A and B? Why isn't it called A? There's actually a reason for this. So the very first personal computers that were released that ran DOS was released by IBM in 1981. It's the 1981 IBM Pc. And it did not ship with a hard drive. Like, if you were to go out and buy it, it didn't come with a hard drive. It only came with 1 or 2 floppy drives. That was the default hardware. And in fact, I don't recall if you could get a hard drive in 1981 when it was released. I wasn't actually alive then. Although I did have this computer. So by default, it didn't come with the disc. You could buy a disc at a later date, but it was an add-on and it was very, very expensive. And it was only 5 megabytes. So the original drive letters are A, which is a floppy. So if you actually had a desktop tower and you put a floppy drive in it, like a 3.5 floppy, it would automatically get assigned A. And then if you added a second floppy, B is the second floppy drive. And then if you added a CD drive, CD drives, which came after the hard disk editions, CD drives usually get assigned D, assuming you have only 1 hard drive. Now, when I got my first 486, I actually had 2 hard drives. So my hard drives were C and D, and then the CD-ROM got called E. And then, like, back in the 90s, the network drive was usually N or Z, depending on how many you had. So, I mean, originally, the Windows file systems only really supported up to 26, because there's only 26 letters, different file systems to connect. But nowadays, you can actually have them named, so it's not like a single letter. You can actually have, like, a proper string here. But that's how Windows handles the virtual file system, is The path name actually is comprised of two components. The first component identifies which file system, and the second component is the path on that file system. Now, Unix systems do things a wee bit different. And how Unix does it is by mounting. So we're not physically going to make a single namespace tree that's like truly combined. We're just going to kind of make it look like the two namespace trees have been combined. So it's not making things into one file system. We're just going to kind of temporarily merge their file system trees. And what we do is when we call mount in Unix, so here's our two file systems. We've got the root and we've got file system X. When we mount, we tell it take file system X and attach it to this directory. And what it does, so we have directory XA, and I am going to have the root of file system X be there, attached at XA. So now to get anything from file system X, it will be prepended with XA. And then if I want to get to XG from X, it's XA, XG. Now what's interesting here is that you're now in this namespace tree technically going to have multiple files with the same I number, but there's no problem here because even though it appears that this is now one file system, they are still technically separate. And as we traverse this path, we will be recognizing the fact that we are, in the kernel, traveling to a different file system. So mounting and unmounting, which is attaching and unattaching the hierarchies, is how Unix does the virtual file system. All right. So I'm going to leave that there for today. And in the next class, episode number 20, we are actually going to talk about the physical file system. So that will be very exciting. We are going to actually look at what's called a very simple file system, which is very similar to ext1, the pre-journaled Unix file systems. So we will see you next week.
Please insert your stolen card now. Pin number.
Will you hurry up? This is taking too long.
Go baby, go baby, go baby. Alright. Pin number 900.
Who'd you learn this stuff from anyway?
From my mom, my real mom, I mean. Withdraw 300 bucks. Come on, baby, come on, come on, come on. Yes!
Hey, it worked.
Alright. Easy money. Come on. Yes!
Yeah!
Piece of cake.
That her?
Yes.
So she's pretty cool, huh?
No, she's a complete psycho. That's why she's up at Pescadero. It's a mental institute, okay? She tried to blow up the computer factory, but she got shot and arrested.
Oh, shit.
She's a total loser. Come on, let's go spend some money.
All right.